Hello, and welcome to this video on periodic trends. So the first thing about periodic trends that we need to know is about electrostatic attraction. And basically that's this whole idea that oppositely charged particles are going to be attracted to one another, and if we have particles that have the same charge, they're going to repel one another. And so it's attraction and repulsion. And both of these are really, really essential to understanding periodic trends. So we have factors that affect the force of electrostatic attraction or repulsion. And the first thing that we want to really look at is the distance that electrons are away from the nucleus. And so if they're further away from the nucleus, then they have less attractive force, and if they're closer to the nucleus for these electrons, then they're going to have a greater attractive force to that nucleus. And so when we have those numbers of as we move away, we're actually decreasing that force of attraction. It's harder for that nucleus to hold on to those electrons. And so inner electrons also are going to shield those outer electrons from that attractive force. So the ones on the inside are kind of spending more time with the nucleus or more attractive interactions with that nucleus. And that impacts the trends that we see for a column. And so as you move down the periodic table, what we see is that first row is the first energy level, and those are going to be electrons that would be the closest. And as we continue to move down the periodic table to that seventh row, those electrons that are in the very outermost in that seventh row are the furthest away from the nucleus. The other thing that we see is that we have a nuclear charge, or a number of protons, in our nucleus itself. And what we know about that is that if we increase the number of protons, we increase the attractive force. And so this comes back to something called Coulomb's law. Okay. So I'm going to use this. So Coulomb's, and we're going to take a look at Coulomb's law a little bit later. And so basically the idea, and you can think of this with like magnets, which is a lab that we sometimes do. And so the closer the magnets are together, the stronger their pull is. As we start to pull them apart more, then that attractive force isn't as strong. And if we were to add like two magnets on one side and one on the other, and then we added a third one, we would actually see that the more magnets that we had, the pull, that attractive force would increase. So now what we want to do is we want to look at this in terms of what happens on the periodic table. And so this first one is atomic radii, or basically the size of our atoms. And what we see, and I'm going to draw my arrows in the direction of increasing, okay, so from smallest to greatest. And so we see the normal trend as we move down a period, and this is what we would expect, is that they increase from top to bottom. But you would think that as they were adding protons and electrons across a row, that would increase as well, and it doesn't. It actually tends to be larger on the left-hand side than the right-hand side. So let's go back to the idea of what we were talking about with Coulomb's law. So as you're moving down, these get bigger as you move down, because we increase energy levels. Okay, so I'm going to put increase energy levels. Okay. However, across the period, we see that as we move from left to right, we're increasing. So as we move left to right, okay, as we're moving this direction, we're increasing the protons, which increases the nuclear charge. And that's making these guys over here smaller. Okay, and so if we're looking at this from a general sense, and it doesn't work for all of them, we always have these exceptions. Okay, from a general sense, what we see is that the smallest radii are going to be up in the upper right-hand corner, and the lower left-hand corner is going to be the largest atoms. Okay. Now, hydrogen is also very, very small, and so not everything follows this trend exactly, but that's the overall trend, and then we have to look at individual data. So the next thing that we want to look at is going to be ionization energy. And so ionization energy is basically the amount of energy it required to remove an electron from an individual atom. And so what we see in this case is it's actually the opposite trend, that it's going to require more energy as we move up, okay, from the bottom to top in a row, or excuse me, in a column. And then as we go from left to right across the period or the row, it's going to be greater. And so the greatest energy, okay, is up here. So greatest energy and the least energy. And again, it comes back to that whole idea that as we move farther away, it's harder to hang on to those electrons if they're further away. And if we have more protons, we have a greater force of attraction. And so as you move across the row, it's going to pull those electrons in a little bit tighter. So across the row, they're not any further away, but they're actually increasing that charge, and so it pulls them tighter. Okay, the final one that we're going to talk about is electronegativity. And with electronegativity, it follows that same general trend that we saw in ionization energy. So electronegativity is the ability of an atom to attract electrons. Now, with that, most of the noble gases are not going to be attracting more electrons to themselves. Now, that doesn't hold true for all of them. Xenon will actually go ahead and bond in some ways, but for right now, we're just going to say they really don't matter. And we see the same overall trend, though. Oops. Let me get that back up here. Okay, so again, we're going to squiggle out these guys, those noble gases. So we're going to see that same trend going up the column or the group, and then from left to right. And so actually, fluorine is the most electronegative. And the way the shorthand for that is going to be En, right? En for electronegativity. So most, and the least is going to be in this corner, so least. Francium would probably be the least there. And the same thing, okay? So they're going to be able to pull more electrons to themselves if they have more protons, and if those electrons are closer to those protons, and so we see something like fluorine is going to be the greatest amount. The noble gases, they already have a full valence shell, and we'll talk about that later, which means they're happy as they are, and they don't usually need to gain any more electrons. They kind of stay stable, and that's not the case for all of them, but especially for helium, neon, and argon, that's very much the case. I hope that was helpful, and we'll take a closer look at this and a couple other general trends on the periodic table in class.